Hello and welcome to Solving Systems of Linear Equations using Matrices. Topic 1 asks us to identify the coefficients and the constants in these given equations. Let's move to the more difficult example, which would be example 2. The coefficients are just the numbers in front of your variables, and the constant will be the number without a variable. So the coefficients in the first equation would be 1, -1, 1, and the constant would be the number on the end with no variable attached, which is a -4. In the second equation, your coefficients would be 1, 1, and -2, and your constant would be a 12. The third example is missing the y variable. So we can force a y variable by n by giving it a coefficient of 0, meaning it really is just 0. But the coefficients would then be -1, 0, and 1, and the constant would be the -5. As we move to topic 2, we are asked to create an augmented matrix. This relates directly to the coefficients and the constant. Again, let's look at number 2 instead of 1. Notice that the first two equations have x, y, and z in them. So the third equation, I'm going to force an x variable in it by just claiming it 0x, which is simply 0. So to make a matrix out of this, you will draw a couple of large square brackets. And in the top row, you would list your coefficients, which are 1, -2, and -2. And then on the end would be your constant. The second equation would be 2, -3, 1. 1 is the coefficient of z, and then your constant, which is -10. The third row would be 0, 1, -1, and the constant is 6. This is referred to as your augmented matrix for that large system of equations with 3 variables and 3 equations. We often put a dashed line in the augmented matrix to indicate where the equals is located in the equations of the system. Another interesting piece of information, which is quite important, is what is known as the dimensions of your matrix. We have 1, 2, 3 rows, and we have 1, 2, 3, 4 columns. So we have 3 rows by 4 columns. This is called the dimensions of your augmented matrix. It is always rows before columns. Let's move down to perform some operations on some matrix, which really we're going to only perform the operations on one row at a time. Looking at number 3, it asks us to find 1/2 of R1. In other words, this would be like row 1 of a matrix. To take 1/2 of it means to take 1/2 of the 0, which is 0, no comma. 1/2 of 2, which is 1, and 1/2 of -4, which is -2, and that would be equal to 1/2 R1, or 1/2 row 1. Let's move down to number 5. It states to compute -2 times row 1 and then add it to row 2. Well, let's come up with -2 times row 1. Here's my row 1. I'm going to multiply every element in that one row times the number -2. -2 times this 1 is -2. -2 times 5 is -10. -2 times the 6 is -12. And -2 times the 2 is -4. That's the results of -2 times row 1. It wants me to add it to row 2, so I'm going to go ahead and write my row 2 here underneath my -2 times row 1. So to add these together, -2 times row 1 plus row 2, I would simply add these numbers in these columns above. I would take -2 plus 2, which is 0, -10 plus 1, which is -9, -12 plus 5, which is a -7, and the -4 plus 1, which is the -3. You wouldn't typically put check marks like that, but I'm writing the check marks so you can see what numbers I'm referring to. This would be the result of taking -2 times row 1 and adding it to row 2. Let's move to our connection to college algebra. It is now asking me to solve this system of equations using what is called the Gauss-Jordan elimination method. In other words, we begin by converting this to a matrix. So I'm going to make my augmented matrix. Actually, I should probably move to the right a little further. I'm going to make my augmented matrix, which is a -5, 2, -17, 1, 2, 1. To solve using the Gauss-Jordan method, the goal is to take that augmented matrix and make it such that we have 1s on the diagonals and 0s above and below the 1s. Now, whatever these values are on the outside, these constants out here, that's what we're looking for. To make this happen, to get a 1 in the top left corner, it would probably be a good idea to just interchange rows. In other words, this would row 1 interchange with row 2 would just result in a 1, 2, 1, and then a -5, 2, -17. So I have the 1 in the top left corner. Now my goal would be to make this -5 a 0, or in other words, add 5 to it. So what I want to do is take 5 times the elements of row 1 and add it to row 2. Now the results go back into row 2, so I'm changing row 2's numbers. I'm going to use a different pen color because that does make it a lot easier. And take 5 times row 1. 1 times 5 is 5, 2 times 5 is 10, and 1 times 5 is 5. So I'm going to take the blue numbers and add them to row 2 and put the result in row 2. 5 plus -5 is 0. That's kind of a strange color. 10 plus 2 is 12, and 5 plus a -17 is a -12. I do not change my row 1 elements, leave them alone. I'm only changing, ultimately, the row 2 elements. Now my goal is to get the second one in the diagonal. The easiest way to make that happen in this case would just be to take 1/12 of row 2 and put those results back into row 2. I'm not even touching row 1 in this operation. 1/12 of 0 is 0, 1/12 of 12 is 1, and 1/12 of a -12 is a -1. At this point, I have the 1s down the diagonal and the 0 in the bottom left corner. I now want a 0 in the highlighted position. So, to make 2 0, I need to subtract 2 from it. So I'm going to take -2 times row 2, add it to row 1, and put those results back in row 1. So ultimately, row 1 is changing. I'm going to change my pen color and multiply -2 times row 2. -2 times 0 is 0. -2 times 1 is -2. And -2 times -1 is +2. Now I'm going to add the blue numbers to row 1 and put those results back into row 1. 0 plus 1 is 1. -2 plus 2 is 0. And 2 plus 1 is 3. I now have my matrix in what's called reduced row echelon form. I'm going to go ahead and write that down, which means I have 1s on my diagonal and 0s everywhere else. Now if I come out of the matrix back to an equation, the top row would say 1x plus 0y equals 3, or x equals 3. The bottom equation, if I take those elements and write them back into an equation, it would be 0x plus 1y equaling -1, or y equals -1. There are my solutions. That method is called Gaussian elimination. Number 2 is quite a bit more lengthy, and it's also a little more difficult. So in this case, I'm going to pull up the calculator and show you how to get the reduced row echelon form of your augmented matrix, which will ultimately give you the solution to this large system of equations. We still begin by writing the augmented matrix using the coefficients of all of the variables and the constant. In this system, it is set up nicely for me. Every equation is in standard form. I'm not having to fill in any zeros anywhere. And here is my augmented matrix. I'm going to enter this matrix into my calculator. So I'm going to pull up a calculator. And this should look something like your TI-84 on the left side. The coloring is not going to be the same, but the keypad should be identical. Everything you're searching for is in this matrix in blue on the left side. Your first column, which must be about row 4, and I'm circling it. I'm going to go second matrix, and I'm going to name my matrix, say A. I'll just pick the first one. Now I need to move over by arrowing over to the edit button. So I'm editing matrix A. Now I'm going to hit enter. So now I'm going to enter all the elements of my matrix, but I need to give its dimension. It had 3 rows and it had 4 columns. Enter. When I put the dimensions in, it will create the matrix ready for me to put the numbers in each position. There was a 1, enter, then a 3, enter, 2, enter. Hold on, that's not right. Let me back up. Whoops. Let me get back over here. See if I can position this thing. Okay, use your arrows to position it back. Sorry. It was a -3, enter. Then it was a -8, enter. Then it was a 12 and a -45, enter. Then row 2 was a 1, enter, 3, enter, 2, enter, 23, enter. Row 3 was 5, enter, 4, enter, -10, enter, and 29, enter. Once your matrix is created, you quit. Second, quit to get out of the matrix and back to your home screen. At this point, we want the reduced row echelon form of that matrix, or the RREF. Go back to second matrix, and now to the right you will see the word math. These are a bunch of options to work with when you're dealing with matrices. I'm going to arrow down until I finally see the RREF, which is the reduced row echelon form. There it is. Now I'm going to hit enter to transfer it to the home screen. My matrix was matrix A. So I'm going to go second matrix, and it's highlighting matrix A, which is the one I just entered in there, and I'm going to hit enter to pull that over. Now I'm going to close the parentheses, and this will now do all the algebraic steps required to get the 1s down the diagonal and the 0s everywhere else when I hit enter. There it is. I'm going to pause in a minute so I can write it down. Now that I'm finished using my calculator, let's go back to our document. And we have just changed that augmented matrix such that the calculator changed that augmented matrix. So it looks like 1, 0, 0, 3, 0, 1, 0, 6, 0, 0, 1, 1. And this is the reduced row echelon form of that augmented matrix. If I convert this back to an equation, this would say 1x plus 0y plus 0z equaling 3. Or in other words, x equals 3. The second row would be, the second row would be 0x plus 1y plus 0z equaling 6, or y equals 6. And the third row, 0x, 0y, but 1z equaling 1, or z equals 1. So your solution is that x is 3, y is 6, and z is 1. Sometimes they will write this as what is referred to as an ordered triplet. And make sure if you write the ordered triplet, you have the x, the y, and then the z. That order is important to represent the solution to that system of equations. I hope this has been helpful, and have a great day.